Assalamualaikum and good morning, my beloved students. So I would like to tell you about seismic interpretation subject. Okay, since I'm taking over from Dr. Maman, let me share with you some fun fact about seismic. So please have a positive view of seismic. That seismic is interesting indeed because you can see things beneath your feet 4 kilometers long and very deep. You can go up to 12 kilometer deep. You can even see some mantle. And the truth is, in this modern world, you can't survive as a geologist or geoscientist without seismic. Trust me. And this is where the money lies. This is where your hydrocarbon reserve are there. Your water reserve can be found in seismic too or in subsurface data. So let's have a look. So for today's plan or the first lecture plan, I would like to share with you the lecture and lab plan for my part. An introduction about myself. Do you want to know? I'm not sure if I have prepared that slide or not. And then I will share with you the assessment plan for my part and also the 2D versus 3D data. That's going to be our first lecture. Okay, that's going to be the lecture plan and tutorial plan as well as my assessment plan. So you're going to see that, so I've put the color in red because we are still not confirmed of the lecture days yet. Hence, I prepared this video for you to watch and learn it prior to our lecture so we can have some more time during the lecture to do more discussions and rather than spending time listening to me only during the lecture. So the first topic is going to be the 2D data and 3D data. What's the difference and advantages of each of them? And then we're going to move to structural interpretation where you're going to see the faults and folds and those structures important for our geology. And then we are going to see interpretation on clastic environment, clastic and carbonate environment. And then we are going to learn about referencing system, which is the coordinate referencing system, and sec-y data, which is how we store our seismic data. And on 9 April, week 13, we are going to have a test during the lecture. While for the lab or tutorial plan, we are going to do data reading and structural contouring, fault picking and characterization, interpretation of seismic on sedimentary environments, and exercise on the sec-y data loading. That's going to be some demo with petrol as well as your exercise on hands-on exercise. So all this has been shown here that you are going to have 2.5% for each of the lab, and the total for the lab is going to be 10%, and you are going to have tests for another 10%. Okay, let's go into the real topic for today, which is seismic interpretation in 3D domain and 2D domain. So as you can see the diagram here, the image here, it is showing the grids of your seismic lines. All 2D lines, when we combine in a volume, is going to be a 3D data. So the increased usage of 3D seismic can be split in between the financial benefits and the quality or improvement of the interpretation. So 3D seismic data is basically can be defined or can be known as a seismic volume made up of series of seismic lines. They are each seismic line compose fixed number of seismic traces, and we have thousands of traces in a seismic 3D. On the seismic 3D, the main component gonna be inline, cross line, and one more thing is the time slice. And you're going to have a huge amount of the data. The size of the data going to be very big. And in 2D, it's going to be only a comparison with 2D. 2D only have CDP, common dead point, and short point. So you can see this is how a volume looks like. So this is how a volume looks like. The top view is a time slice, means you're gonna see things on a plane view, and then this is your cross line, this is your inline. So you're gonna have X, Y, and Z. So a 10 to 10 kilometer 3D survey at a distance of 25 meter line spacing contains 400 to 400 times 400 traces. So the amount of the traces is gonna be 160k traces. And the majority of the 3D surveys now have line spacing of 12.5 or even shorter spacing, and resulting in 640k traces per 100 kilometer square. So just imagine if you have 1000 kilometer square, how much of your traces you have to interpret. That's going to be only in the traces, but in the time domain, you are recording it at every 4 milliseconds or every 2 milliseconds. So a single trace covering 4 seconds in times equals to 1000 times traces, resulting in 6.4 times 10 to the power of 8 samples for our 100 kilometer square 3D seismic survey. So for each sample, either in 8 bytes, 16 bits, 8 bits, 16 bits, or 32 bits, and so on, the digital storage required to record the amplitude is huge amount. So the amount of data or volume to be interpreted for a 3D data is actually number of inlines times the number of cross lines times the number of time samples and number of data types, means what domain you are interpreting it. So how do we view it actually? The 3D seismic volume can be sliced in any direction. We can view it in 3D or made semi-transparent. So as examples, you can see you have a cross line, inlines, you can view it in time or depth. You can pick your horizon and then view only your horizons or only your surface. And then you can also do random line to connect some points that interested for your interpretation. These random lines are picked in the software in a 3D mode. This is examples of the characteristics or the attributes belongs to 3D seismic data volume. Of course, you're going to have inline, cross line, so arbitrary lines, which is the line that you connect 2 points, that random points, and imaginary line, something like that. Spacing interval, time in second, time in milliseconds, sampling rate, the data volume. So the orientation, here we did not include the time slice. So the time slice is gonna be at the top view at every millisecond that you would like to see. And this is how data loading looks like. I just give you an overview because you're going to have one topic for this later. So the 3D data is in ZY format. So you have to input all this before you can start loading. So this is usually the most time consuming part in loading the data. So we need a big workstation, a powerful workstation. A small laptop is not enough, but a good with graphic card with enough memory, that will be enough. This is because you have to manage a big amount of the data. You have to digitally store the data in any position, travel time, and value of the amplitude and other attributes. So you need to display your data in different formats. Sometimes we have to display it in a wiggle format, in density format, and so on. So using a good workstation can allow you to flatten your seismic data, allow you to do automatic horizon picking, automatic fault picking, and so on. So this will actually be very costly, because a good high performance workstation is roughly cost minimum 10,000, and it can be more than 20,000 if for a company or industrial usage. So how long does it take to complete your interpretation in 3D domain? So you're gonna do a data loading, and then you do a preview like a QC or quality control, choosing the best display for your interpretation. Then you're gonna start your basic interpretation of your picking the horizons, picking the faults, and you have to refine your interpretation because sometimes you did it wrongly, and then you need to have someone to verify for you. You have to create an isopac maps, a depth maps, surface maps, and so on. So we are going to learn what is isopac, what is surface map in later. You have to apply attributes analysis. So we are going to learn attributes in third year. You might be lucky if you're going to see me again because I'm going to teach you seismic attributes in third year. And then you have to do a further detailed reservoir study, to do upscaling or downscaling of your results. And this can take several months and years and involve a big team of geoscientists, reservoir engineers, and so on. So let's see the advantages of 3D over 2D seismic data. So of course, the spatial continuity improve in 3D data. We have a correct positioning due to 3D migration, so we don't have the smiley effect in 3D data. Not we don't have, we do have, but it is less compared to 2D data. So this is showing the results of 2D and 3D for the same particular location of lines, where just the acquisition has been improved from 2D to 3D domain. So you can see that we can have a better image of the reflectors in this rectangular compared to the one in 2D. And in a map view, let's say you are producing a structural map. So you see in 2D domain and in 3D domain, the results, the 3D data, the result shows that you have more segmented and more elongated faults compared to the 2D structural map. So you can see the faults are only 1, 2, the major faults are only 1 and 2 here. But here we have 1, 2, 3, and we have more segmented. So you can see that your reservoir are very compartmentalized compared to when you produce the same result using 2D data. So as I mentioned just now, the spatial continuity improve, correct positioning, line spacing is smaller, so you have a better horizontal resolution. You can provide as many seismic attributes you would like to apply, and you can do application on the horizon slice, and this can improve seismic geomorphology study. So the same data in 2D and in 3D, you can see is a lot of improvement. You're going to see an anticline rather than lots of noises in the 2D data. And you have high accuracy in seismic picking. It can use the advantages of auto tracking for the seismic horizons. You can extract the amplitudes in grids straight away. When you load the data, you can generate random lines or imaginary lines quickly and easily. So these imaginary lines or random lines can be helpful for you to connect your well location and so on. You can also do interpretation in time slice or horizon slices, which is you can see the top of it. And then it is very good for reservoir characterization and model building. So this data showing the 2D data in 1983, and 11 years later when we do the acquisition in the same area with 3D technology, you see we can see improvement of faults. You see you have some lineament here, but this one is really good. You have a closely spacing faults, you have a good reflectors, you have more faults in the deeper part, and you see this is superb. So the difference of 2D and 3D is in terms of how they acquire the data, how they process the data. So I'm going to have a short briefing on how 3D survey has been done, the acquisition and the processing. I'm sure you have learned this in seismic methods, right? So the 3D survey, the objective is to image the area